Okay, so today I'm going to talk about the. Actually, as I explained last week, right? I'm going to skip this topic for a while. This residual diagnostics, right? And we'll skip this. This is a little bit advanced topic, so I may get back to this later, right? So and then. So I mean the Cook's D chart, yeah, this is an important topic, but I'll skip it for now. And then I'm going to talk about this section, improving the model. The first one is considering the nonlinear relationship. So as we can see, right, um, if you look at the rentals versus the humidity, and the rental versus the wind speed, and rental versus the temperature, right? When you look at this, I mean, this line is a straight line, right? This is a straight line, right? This is straight line. However, our assumption is basically what? Our assumption is in our previous model, right? Our assumption is that the basic assumption is that the relationship between the predictor, right, and the response variable, like response variable in this case is rental, right? It's a linear, right? So this is like basic assumptions. However, this is not always the case, right? This is not always the case. For example, looking at the plot in this, right? If you look at these plots, right? If you look at the rental versus humidity, right? You know that this is not really straight, line. This is more what? This can be explained with this line, right? You know what? I'll use the blue. So you know that this is probably the better fit, right? And same for the wind spread. It looks like by looking at this plot, it's probably the better to use this blue lines, which is not a straight line, right? And you know that this green line, right? This is more like the polynomial relationship. So this blue, red, and green represent the fit, right? Represent the fit with the polynomial predictor introduced. So the key point is polynomial predictors. As you can see, this is not really straight line, right? This is like more like a polynomial, right? Okay, so for that reason, right? For that reason, this model introduced another variable, right? So we're gonna use humidity multiply, the square 2, right? So it's so this notation means polynomial relationship, okay? So what we are going to do is we are going to add 3 additional columns, right? So looking at the curvature of the colored fit line, the curvature, right? They seems to suggest the quadratic relations. So we're gonna use a quadratic relations. So we'll add a square version of the predictors to the model, right? And to do this, we simply create new variable, humidity 2, wind speed 2, and the temperature 2 as follows. So they are going to use a mutate, right, to add new column called humidity 2, right? So this is going to be the new column. And then they're using this square 2, right? It's for the what? For the quadratic relations, right? So same for the wind spread, right? This is like power 2, right? So this is what? This is the quadratic this is for the quadratic relations, right? And so you know what? Basically using the mutate, right? We add these 3 new variable, right? And then the value will be filled with what? Quadratic value, right? Okay. So then in the new model, right? And then so this is a bike 2. This new bike 2 now what has these 3 additional columns: humidity 2, wind spread 2, and column 2, right? That's a bike 2. And this is a bike 2, right? Okay, so hold on. so this is better. So you know that this is bike 2, right? So this is now has these 3 additional columns, and then we look at this bike 2, right? And then we create a new model, bike 3, right? So we use LM functions, and then this is what? This is the response variable, target variable, and y. And then we're gonna look at a couple of so we're gonna look at the 3 additional the variables, right? The independent variable, the 3 additional predictors: humidity, wind speed, and temperature, the one that we have. And additionally, right, we'll have humidity 2, wind speed 2, and the temperature 2, right? So this is from here. Right, okay. So when you look at the summary, right, the result is this. Is pretty much everything is really significant, you know, because the p-value, it's really small, right? So these are the various these are significant, right? And now look at the humidity 2, which is a new added column, new added predictor. And then this is significant. It's good. So this is good. And then let's look at the temperature, right? Let's look at the temperature. And temperature 2 is a significant, right? It's less than 0.05. It's less than what? 0.05, which is a 5%, right? 5%. Okay. However, look at the wind speed 2. This wind speed 2 is, the p-value is relatively big, right? 0.6. So 0.6 is definitely greater than 0.05, which is 5%. And you know that there's nothing. So this is what? This is not a statistically significant, right? So we should get rid of this, right? So we should get rid of, you know, this. Okay. Now, having said that, so we are going to build a new model, right? Which is wind 3. In the winds by model, as you can see, we only have a humidity 2 and temperature 2, right? We eliminate, as you can see, we eliminate this wind speed 2, right? This polynomial regression, right? I mean, we added this to represent this polynomial regression model, right? But this wind speed number 2, it's not really statistically significant, so we're gonna get rid of this. And as a result, right? As a result, we have a humidity and wind speed, and then humidity 2 and the temperature 2, right? As we eliminate wind speed 2, and now let's take a look at this result, right? And when you look at the result, everything is what? Everything is now is a significant, right? And then you know, the residual standard error is 1012, right? 1200, about 1000. Okay, so now let's just compare. So this is like a better model, right? So let's see. Oops. It's very hard to draw using the mouse. It's not easy. But anyway, I'll do my best. Okay. So this is a previous model without. Okay. What? Wind speed 2, right? So this is wind speed 2, and this is like read. And then the next one, the new one, is without wind speed 2, right? And we know that it's the residual standard error is about 1200, right? So this is like a what? Residual standard, right? Error, right? Residual standard error is in the second case is what? 1,000, 1,200, right? Around about, right? And then the r squared, right? I mean, actually, let's look at the adjusted r squared, because we need to look at the adjusted r squared because we are going to compare, right? Compare these two models. Read wind speed 2 and without wind speed 2, right? So we are gonna comparing these two models, and that's why we need to use adjusted r squared. And adjusted r squared is what? 0.59. It's about 60%, right? So 0.59, right? 0.59, right? Now let's look at the previous one. Just scroll up, and residual standard error is 1,000. 1,1213. I guess I have to be really precise to compare. So this is what? 1,013, right? And then the adjusted r square is 0.5988. So it's not much really difference. Let's see. But I have to be precise. 5, 9, 8, 8, right? And let's just scroll down. And okay, so this one is 0.5933. So I have to really 993, right? And this is the 13, right? Okay, good. The residual standard error is 1213, so I have to really precise 13. Okay. Now, so if you look at this, compare the previous model, right? Okay, so if you look at the the previous model and the current model, so this is like without, so this is without wind speed 2. If you look at the r residual standard error, it's about the same, right? It's identical. 1213, 1213. So this is identical. But now I think we have a little bit of improvement, right? So previously we have adjusted r square value is what? 5988, and with the new model, right? I'll say the improved model, right? It's what? 0.993. So this is a little bit. This value is a little bit, larger, right? So that means yes, the model has been improved. Well, but it's not really significant. But still, yes, it's improved, right? Because one is what? 5988, and this value is what? 5993. Yes, so there's some minor improvement, right? Okay. However, right? When you look at the without, okay, so maybe we should have another. Maybe it's a good idea to look at the another model, right? I'm gonna draw the another model, right? So the another one is now what? Another one is without this polynomial regression model, right? So we know that we introduced a polynomial predictor, right? And let's say without polynomial predictor, right? So let's just take a look at the old model. Okay, let's see. Yeah, so this is one, right? This is the let's say, okay, so now we know that it's, as you can see, we have humidity, wind speed, and temperature, right? So this is without the polynomial predictor, right? In this case, the residual standard error is 1,425. So this is 1,425, right? And then the R square is 0.45. So this is 0.45, right? Okay, so this is, okay, so good. So I'm going to just delete this. Okay. Yeah, so let's take a look at this. Let's look at, so this is what? The first one is, you know, just simple, like multiple regression line with without, okay, so without, oops. So this is what? This is the, so this is without the polynomial, right? Polynomial. So without the polynomial, right? Just with this simple three predictors. So without polynomial predictor, you know the standard, the residual standard error is pretty big, right? Pretty big compared to. So let me just use the. So this is a pretty big, right? This is pretty big compared to this value, right? This is pretty big. So that means it's good to have what? Good to include the polynomial predictor, right? It's good to have because this error, standard error, it's the residual standard error, it's much greater, right? So this is like an average, right? An average for each observations, you know, your standard residual error is what? 1,400, right? And whereas this residual error is only what? 1,200. So this is like, this is much better, right? So you know that this two is with the poly, right? With the polynomial predictor, and this one is without the so this one is without the polynomial predictor, right? And now let's look at the R squared, adjusted R square value. This is what? 0.5. And this is what? This is a 0.5993, right? So this is what? This is much better, right? So in that regard, this polynomial regression model is much better, right? So it's good to include this two additional polynomial predictor, right? Because, you know, the variability in the response variable, like rental variable, can be about, you know, 45% of the variability in the response variable can be explained in this model, right? Only like 45%, but in this one it's close to 60%, right? Close to 60%. So this particular model can explain the like 60% of the variability in the response rate. So that means it's much better, right? This is much better than this one, right? Without polynomial predictor. Okay, so that's how you should interpret this result. Okay, so thank you. Yeah, so I'm going to next lecture, I'm going to introduce another way to improve this model, right? There's another way. Okay, so I mean additional way. Okay, thank you.